Hey y'all, welcome to 6.1 Linear Approximation. This is probably the easiest notes of the entire year. I know you're excited. Let's get to it. So linear approximation is the process of using tangent lines to get an approximate value for y at non-integer x values. Okay, so we use linear approximation to basically make an estimation, to approximate values on a curve using that tangent line. We're going to see this when we kind of draw a picture over here on our graph. Okay, so for number one, function f of x is a differentiable function whose first derivative is given by f prime of x is equal to 3x squared minus 12x. Find the following. Write the equation of the tangent line to the graph of f of x at the point 1 comma negative 5. Just a reminder, our tangent line equation is y minus y1 equals m times x minus x1, that point slope form from algebra 1. So we have our point, we have x1 and we have y1. So x1 equals 1, y1 equals negative 5. We do still need our m, and remember we get m from our derivative, so m is equal to f prime of x. So f prime of 1 is equal to 3 times 1 squared minus 12 times 1, which is just 3 minus 12, which is equal to negative 9. Okay, so all good so far. We have x1, we have y1, we have m, so now we can plug that all into our equation. So y minus y1 is just plus 5 equals negative 9, x minus 1. Okay, so all done. Okay, part B, we want to use this equation of the tangent line to estimate the value of f of 1.1. So you might notice we don't have f, we only have f prime. F prime of x is equal to 3x squared minus 12x. So we're going to use our tangent line to estimate a value on the original function. So it's kind of like using our derivative to estimate values of the original function. It's really, really cool. So all we got to do is we're going to take 1.1 and we're going to plug it in for x in our tangent line equation. So y plus 5 is equal to negative 9, 1.1 minus 1. And you would be like, Mr. Bone, that seems like a number I'm not going to be able to work out easy. But it actually is, they're always going to give you numbers you should be able to do with a calculator. So 1.1 minus 1 is just going to be 0.1. So y is equal to negative 9 times 0.1. I did go ahead and move that 5 over because I want to have y by itself. Negative 9 times 0.1 is negative 0.9 because I'm just multiplying 0.1 times 9. So y is equal to negative 0.9 minus 5. And then negative 0.9 minus another 5 is just negative 5.9. Okay, so that is linear approximation. Linear approximation is just writing an equation for the tangent line and then plugging that value into your tangent line that you solve. So A and B is linear approximation. Okay, that's in a nutshell. The little extra step that they're going to add in is determining if the estimation in part B is greater than or less than the actual value of 1.1. So if you forgot, we did this a little bit with our Riemann sums where we added in that overestimation, underestimation. This is kind of like the same thing. Is this an overestimation or underestimation of our actual value? I'm going to show you two ways, graphically and analytically, and then you might think I'm going to let you choose, but really you shouldn't choose the graphical way. You should only choose the analytical way because the analytical way makes way more sense. Okay, so let's look at part C. So part C, determine if the estimation in part B is greater than or less than. We're going to start with graphically. Okay, so for graphically, we do want to go ahead and graph this equation. And I'm going to go ahead and cheat and just give us our value of f of x, which f of x would just be x cubed minus 6x squared. And I would, of course, find f of x from f prime of x by integrating. And then, of course, I'd get plus c. I'd have to plug in, get that initial condition. Plugging in, we actually get a value of 0 for c, which is why we just get the function x cubed minus 6x squared from 3x squared minus 12x. Cheating a bit because I don't want to make this video super long. So x cubed minus 6x squared. If you can graph this, awesome. If you can't graph this, Not that big of a deal. I really am just using the graphical situation to kind of show you the picture. Okay. So if we were to graph this, it's kind of an ugly one, but it does graph like this kind of messy little cubic function where we only really see about this much of it, and that is the grossest line. So we're going to try that again. And it does eventually come back up like over there, that way a bit. Okay, so that is our function. And our point is at 1 comma negative 5, which I went a little bit too far over. I'm having a rough time drawing this graph. Yeah, more like that. Okay, so our point is right here at 1 comma negative 5. And our tangent line equation is y plus 5, negative 9, negative 1. So our x value is 1, our y value is negative 5, so it should go through that point. And then it has a slope of negative 9. So negative 9 is a pretty steeply negative slope. So our tangent line really is going to kind of look like this bad boy. Obviously, that is not perfect. Okay, but that should give you a good enough picture of now, you all tell me, is that above or below the curve? Well, it is definitely above the curve, which means any approximations along that tangent line, because it is above the curve, are going to be over approximations. Okay, now you might be like, Mr. Arbone, that whole graphing process looked convoluted and messy. I have no idea how to repeat that. Like, you had to have used a calculator, which I did. I cheated because x cubed minus 6x squared is a hard function to graph off the top of your head. Well, the good news is we have some calculus that can give us the same result without all the stress of having to graph it. So you might notice on our graph, what nice, beautiful calculus shape does that graph create? Well, it has a nice concave down shape. And if you remember, we described the shape of concave down as portions of the graph where the tangent lines lie above the curve. So if we could prove that our graph was concave down, then we could prove that all of our approximations are going to be over. And if we could prove that the graph was concave up, then we could prove that all of our approximations were going to be under their real value. Okay. Well, we just so happen to be able to do that with calculus. We can prove that a graph is going to be concave up or concave down by looking at the sign of its second derivative. So if this is my first derivative, f prime of x is equal to 3x squared minus 12x, first thing I need to do, I need to find my second derivative. So f double prime of x, 3x squared becomes 6x, 12x becomes just 12. So that is my second derivative. I want to evaluate it. I don't actually have to evaluate it 1.1 because more than likely, I'm not going to switch concavity between 1 and 1.1. So I can really just use the original point to make it a little easier to plug in. You can use 1.1 if you want to be absolutely sure, but 1 is fine. So I can plug in 1. So f double prime of 1 is equal to 6 times 1 minus 12. So f double prime of 1 is equal to negative 6. So because my second derivative was negative at 1, that means my original function is concave down, which means it is going to be an over approximation because concave down means tangent lines lie above the graph. So just like I would anytime I'm kind of analyzing something or proving something in calculus. So f of 1.1 is an over approx, and of course I can be a little shorthand with it because f double prime of 1 is negative, therefore f of 1 is concave down. So because it is concave down there, it's going to create an over approximations for its tangent line equation. So concave down, over approximation, concave up, under approximation. Negative on double prime, concave down, positive on double prime, concave up. Good old calculus house coming back to save the day. So let's look at another example real quick to finish up. So number 2, function f of x is a differentiable function whose derivative is given by f prime of x is equal to 12x squared minus 4x. And we're going to go through the whole shebang. Find tangent line equation, estimate the value, tell me if it's an over under. So first things first, we want to write that equation. We have x1 is equal to 1, y1 is equal to 8. We do need to find m, which of course we get from f prime of our x value. So f prime of 1, which is 12 times 1 squared minus 4 times 1. So 12 minus 4, which is just equal to 8. Y1 and m, same value. So y minus 8 is equal to 8 times x minus 1. And that is our tangent line equation. Nice and easy. Okay, second thing, using that equation of a tangent line, we're going to estimate f of 1.1. So I'm just going to plug 1.1 straight in. So y minus 8 is equal to 8, 1.1 minus 1. So y is equal to 8 times 0.1 plus 8. So y is equal to 0.8 plus 8. So y is equal to 8.8. So that is my approximation. That is my value of f of 1.1. All right, 2 down, 1 to go. So for part C, determine if the estimation in part B is greater than or less than the actual value of 1.1. So now I need to go forwards. I need to go to the second derivative. So f double prime, taking my derivative, f double prime of x is equal to 12x squared becomes 24x. 4x becomes just 4. I want to find it, and I can do it just at 1. I can be a little lazy. So 24 times 1 minus 4 is equal to 20. So that is positive, which means it's going to be concave up, which means it's going to be an under approximation. So f of 1.1 is an under approx because f double prime of 1 is positive, therefore f of 1 is concave up. Okay, so remember, you do not have to write me a full paragraph with these kind of things. You just got to give me that short and sweet little bit of the information I need. Okay, I need to know that you know it's concave up. And because it's concave up, that means it is an under approximation. All right, y'all, that is linear approximation in a nutshell. Super easy, kind of building off of stuff we already know how to do, or at least, 2 parts of it. We really only added one new thing. But yeah, 6.1 in a nutshell. Get to it.